In a multi-node Active Directory environment, thousands of servers share a single database. Keeping that network functional requires managing constant, invisible shifts of data across a massive, highly distributed geometry. To keep this environment synchronized, a destination domain controller must be able to request exactly the changes it is missing without pulling down redundant data it already has. Conversely, the source domain controllers must independently verify exactly what data the destination has already received before packaging a response. Relying on a global timestamp to order these events introduces severe network latency and clock drift. To solve this, Active Directory eschews global timestamps entirely. Instead, the architecture uses a structural solution known as the update sequence number, or USN. The USN is strictly a 64-bit local counter. It is maintained independently by every single domain controller in the forest. By examining how this single 64-bit counter is fragmented to track system state, we can map the exact architecture of Active Directory replication. The system derives 3 discrete metadata tags from the central counter: the local USN, uSNChanged, and the originating USN. By abandoning global timestamps in favor of these localized, multi-tiered sequence numbers, Active Directory creates a mathematically infallible, self-contained ledger of state changes. To understand how this ledger operates, we first transition away from the wide network topology to look at the architecture of a single, isolated source domain controller. In this namespace wireframe, the root DSE is at the absolute top. Isolated from standard data structures, it has no hierarchical name or schema class. Instead, it holds attributes identifying the domain controller, most critically, the highest committed USN. The trigger condition is strict. The start of every single update transaction initiates a change. This trigger applies equally to local originating rights and replicated rights. At the transaction start, the domain controller increments its current USN, mathematically associating this new value directly with the update request. Because of this strict relationship, the root DSE functions as the absolute local master clock. No data modification can occur on the node without permanently ticking this central counter forward. From the top of the namespace, we shift our perspective downward to target a specific user or computer object deeper inside the directory undergoing an update. This table details the object's properties. To track modifications, the incremented master counter value must be stamped onto the modified data, creating a local USN, stored directly in the metadata of each changed attribute. This value is strictly local to the domain controller where the change occurred. Multiple consecutive updates to different attributes on this object create a scattered array of local USNs. Active Directory resolves this clutter by introducing uSNChanged. Mathematically, uSNChanged is the absolute maximum local USN among all an object's attributes. Its critical architectural advantage is that it is an indexed attribute. Because it is indexed, the domain controller can enumerate objects strictly in the order of their most recent attribute right, bypassing scans of individual metadata. This indexing process has one specific edge case regarding forest functional levels operating at Windows Server 2003 or 2003 interim. In this functional level, discrete values of linked, multi-valued attributes can be updated individually without overwriting the entire attribute array. To manage this, the metadata mapping associates a distinct uSNChanged variable with each specific link, in addition to the parent object's primary uSNChanged value. There is a strict boundary. Updates to these individual link values explicitly do not affect the local USN. They only update the uSNChanged attribute on the object itself. Together, local USNs provide granular per-attribute historical tracking, while the indexed uSNChanged provides the rapid query mechanism required for real-time synchronization. We can now pivot from static local storage to the active preparation of a network transit payload. When a source domain controller prepares to send an update, local counters like local USN and uSNChanged are stripped away. Tied to a specific root DSE, they are meaningless to the destination node. Finally, the system attaches the originating USN. This tag has a strictly restricted application. The originating USN is generated only during an originating write. It is never generated during a replicated write. Unlike local metadata, the originating USN is replicated across the network. It travels permanently alongside the attribute's value. This permanent pairing ensures that no matter how many hops an update takes across a forest, the definitive origin state of the change is never lost. The originating USN acts as the immutable passport for the data. It decouples the update's history from the localized clocks of the nodes it passes through. Re-establishing the wider network view, the destination domain controller comes back online to initiate a replication cycle with the source. The destination queries the source, specifically asking for any changes that have occurred since its last successful synchronization. Looking at the source, it processes this request by targeting its indexed data immediately, avoiding a full database scan. The source uses the USNChanged index to rapidly filter and isolate only the objects modified since the destination's last known USN. The source then finalizes the replication payload, containing only those specific attribute deltas. And as packaged, this payload carries the originating USN to prove exactly where these specific deltas were born. The delta payload then transits across the logical namespace gap between the source and the destination domain controller. Upon receipt, the destination unpacks the data and triggers its own originating write process to log the new data. The destination domain controller now increments its own root DSE master counter, stamping its own new local USN and USNChanged values onto the received object. This complete transaction lifecycle illustrates how the global concept of tracking time and state is managed by splitting responsibilities between local indexes and traveling metadata. By architecting metadata this way, Active Directory achieves massively scalable, strictly ordered, delta-based replication across thousands of nodes without ever requiring a single system-wide clock.